All right, we are going to go ahead and get started. To my ASCO people, I'm going to ask if you guys can keep letting in people from the lobby as we are getting started. Thank you to everyone for attending the second of ASCO's e-Lunch and Learn series. This is a regular learning series where I will be providing virtual lunch and learns to the local engineering community on topics relating to emergency power distribution equipment. Daniel, can you go to the next slide? All right. I start off with a brief introduction before all the presentations. For those who do not know me, I'm Mumtaz Farouk. I'm the consulting engineering specialist for the DC, Maryland, and Virginia area. I've been with Schneider Electric for 7 years, 2 of those with ASCO Power, and 5 years on the Square D side. So I've been exposed to different market segments and different sides of the normal and emergency power side of both the equations. Next slide, Daniel. All right, so for today's presentation, we're going to be building on our last one. Last month, we had a presentation on onboard paralleling versus traditional paralleling gear. We touched on some traditional paralleling gear characteristics, which I said we will revisit at a later time. And so today we are going to really build on that and delve into the traditional paralleling gear. Please feel free to utilize the chat for any questions. We do have a lot of information to get through in a 1 hour time span, but we will get to your questions on the chat, and I will have my contact information at the last slide for follow-up, and we will follow up to any questions we don't get on the chat today. I'm going to stop talking. I'm going to hand it over to Daniel Barrios, our solution architect, for the presentation today.
Thank you. Good afternoon, folks. Two things. Number one, I cannot see the chat side. If someone raises their hand, please interrupt, or Mumtaz, if somebody can catch that for us. Mumtaz
I can see the chat. I had muted everyone for the call today. I'm sorry. We had some interruptions last time, which that's fine. Just so we can get through all the material in the hour we have. But I will monitor the chat, and I will get to your question via email or something if we cannot answer on here.
That's fine. Thank you, ma'am. My name's Daniel Barrios. I've been with ASCO really starting back about in 2000, degreed electrical engineer. And just to kind of give myself away, I sort of started in the standby power business all the way back about 1987. I've been in this role now going on 1 year, but as I say, have been with ASCO basically since the year 2000. Following up on what we did, we're going to look at paralleling switchgear. Now, I might repeat some things that you've heard previously, but in the case of traditional paralleling switchgear, as you can see, this is a 3-gen set lineup with a set of distribution. There's a master section. There are individual generator sections. We can do some other schemes to make it fit into your room better. We are taking responsibility. We are taking the outage of the utility. We will initiate as we go through this presentation. We will tell all 3 generators to start in order to make sure at least the first one gets online and able to meet your life safety loads in 10 seconds. We'll delve into that a little bit more deeply. So the paralleling switch gear, a few things we're going to touch on. Number one, by the configuration of the gear, the size of the main bus, the interrupting capacity, whether it be 65, 100, or 200K type interrupting, you need to work with us because that may impact the size of what the paralleling switch gear will end up being. The comment of an N+1 is that in your design, you need at least 2 of the generators online. You obviously have the third one for a bit of more redundancy, belts and suspenders, a greater capacity, maybe even for future growth or so. When we are speaking about paralleling switch gear, okay, I really need you to work with the genset manufacturer's sizing criteria. And what I mean by that is you have to understand that when the first generator hits the bus, we are calling this dead bus arbitration, okay? We are going to have all 3 of the generator breakers open. When we have an outage, start all 3 generators. By the laws of physics, one will hit first, locking out the other 2 momentarily. However, as soon as that first generator hits, it is going to immediately have load transferred onto it because all of your 10-second life safety loads, Article 700, need to be on in 10 seconds. You need to be sure that that's if there's not equal size generators. You have a 500 and two 1000s. If that 500 is the first one to hit the bus, it may be overloaded depending on what that priority one load is. Okay? We're going to run all three generators until we realize we don't need to have that much power. We're going to talk about load control. We're going to talk about bus optimization in many of these slides. So when you look at a set of traditional paralleling switchgear, we basically have a few sections here. In the generator control, there is a master control section that will have a master PLC, either a single or a redundant. Normally, we would suggest a redundant PLC, however, single I/O. If you want additional support in that regard, just in your specification state that you want the redundant PLC and you want redundant I/O. But also along with that, each one of the generator sections in a traditional piece of paralleling switchgear is going to have a generator PLC, and we're going to explain why. The generator breaker is included, obviously protective relays. You're going to see a lot of the generator mounted controller. And then what you're looking at in that first left-hand side, that is a Woodward DSLC, digital synchronizer and load control. When we are doing that, we are taking the responsibility. We are sending a bias signal to your generator set controller for voltage and for frequency, raise lower. When you are retrofitting a set of generator sets or a system that has older generator sets, it is not uncommon that we're going to reach out to you and say, what is the vintage? What type of controller is on there? And also, you may need to update the controller on existing generators. You may need to update the voltage regulator or such, depending on what type of system you have. On a very important note, when you are looking at paralleling generator sets, to go onto their side for a minute, you need to understand a term called pitch. Pitch, pitch. When you wind the generator on its nameplate will tell you it's a 2/3 or a 5/7 type pitch. If you do not have all of your generators of the same pitch, you are going to have circulating current that we can attempt to minimize, but we will not be able to remove it completely. So therefore, if you are adding a generator to existing generators, please work with your manufacturer to be sure you have the same pitch. In the master section, we've touched on the master PLC and I/O, the distribution breakers, tie breakers, utility breakers or such, protective relays, and then specifically if you either have a set of split bus, meaning a bus A and a bus B, or if you are parallel to the utility, we will now have to introduce a master synchronizer, an MSLC, to perform that task. Over on the other side, there is a user interface. You'll see a better picture of it. And again, the same devices are shown. Many times with the trip units now shown, we are typically using the square D type breakers, NW, MTZ. We can get information directly from the trip unit also. But many times we run that through our system and use the user interface panel in order to get that type of information. Looking at a little bit of layout, let me explain one thing to you. When you are looking at your manufacturers, whoever is in your specification, you need to look at the sizes of their sections. Typically, we are very consistent between all of the major manufacturers. There may be a single generator control section. You may also have a dual generator control section, which we have a picture of a little bit later on. We will always need to provide a master control section. The distribution, when you are explaining to me what you want in your system and how you want it to operate, please let me know if those are or if those are manually operated breakers or if you need those electrically operated. Well, why do we need to know that? As you can see in this photograph here, one of the sections of that 4-high cubicle cannot be used with breakers because that's where the controls go into. Just an item to work out with Mumtaz as you're putting your project together. On the right-hand side, well, let's go back a minute. Everything on the left-hand side is considered 600 volt, 120, 208, 240, 480. All of those are a 600 volt class. When we move to the next one, we go to medium voltage, and that can either be 5,000 or 15,000 kV. We also manufacture that type of product also. We also can offer medium voltage transfer switches if you've never heard that or if you're curious. If you look on the left side, you notice that there can be potentially 3 to 4 breakers put into a distribution section with low voltage, 600 volt. When I move over to the 5 or 15 kV class, I am limited to 2 breakers, or I'm limited to 1 breaker and then housing the potential transformer or such in the upper section. What's in the low voltage control? This is a generator control section. We once again are speaking about the PLC. Right now we're using a Modicon. The digital synchronizer, this product is a little bit more updated. I think it's the 2 Plus now or such. The circuit breakers. When you look at paralleling switchgear in low voltage, you can either have that labeled as UL 891. Now, in UL 891, you can use fixed mounted breakers. You can use 489 breakers. Once you've gone into a UL 1558 type application, now each compartment is individually built so that you can't see between each of the cabinets. You now need to have draw out circuit breakers, 1066 breakers. You cannot put 489 breakers in that. But conversely, if you're building 891 construction, you can exceed it. You can put 1066 breakers in. You can exceed it, but when you're at 1558, you cannot go back to fixed mounted. The control section here we'll go into, but this is what's operating the synchronizing. You'll also notice that we have a mushroom there, the emergency stop push button, that can be provided in the paralleling gear if that's what your specification, so that you don't need to run out to the generator set in order to punch the emergency stop button. Low voltage designs here with the dual generator section. Now we went from this section here, we're looking at this one here now, and in doing so, we've reduced your elevation view, your footprint by one section. You can see though that when you go back to the other, we have some analog meters, we have some additional status panels and such. You may lose a little of that functionality and will be relying on the OIT screen, the operator interface terminal, that you can gain some of that information. However, the main thing is that up to a certain ampacity, we can do this. I understand architects never want to give you folks enough room to put things into. Please work with us. Another thing we can do, and I believe it's pointed out a little bit later on, we can either put all of the gear in one lineup, starting from the master section, generator sections, and distribution. If that doesn't fit in your room, we can do segregated controls. We can segregate the master. We can segregate the generator controls. Well, that may help in floor space. The other thing you may want to consider is arc flash. If I'm operating the gear standing in front of it, even to the side, I'm within an arc flash area. For safety, you may want to carry that set of controls outside of the area, or at least to another area in the room or such. The programmable logic controller is in each one of our generator sections. Again, we do provide a synchronizer, breaker, and control switch, even in the dual generator control section. When you look at the topography of what we're dealing with here, you can see that we have redundant load sharing controls and redundant communication controls and such. When you go to our factory to do a factory witness test, which I highly recommend if you have the opportunity to do so, they're not only going to operate the gear for you, but in each of our sequence of operation, there are criteria of failure. Well, what if one landline suddenly goes out? We have a landline B that will pick up immediately. These are hot swappable PLCs, at least when you have the redundant type PLC, okay? When you lose one of your load sharing lines, There is a redundant load sharing line. Load sharing between engines is necessary to avoid overload. Yes, I can parallel a 1 meg generator with a 2 meg generator because what I'm going to do is I'm going to load it percentage wise proportionally to its amount. So if I load the 1 meg at 50%, I'm at 500. Obviously, the 2 meg, I'm at 1,000. And those two float together where we are not trying to put 2 megs of power onto the 1 meg generator. Consider utilizing synchronizing devices. Include load share. Yes, this is an enhancement that I think is something that will give you much more single point of failure, removing some of that. The load sharing connections are redundant and Ethernet. So when you look at the power controls architecture, dedicated PLCs for each generator, as we said, provides engine start. Okay, now we're touching on some things that you folks need to be aware of. According to the National Electric Code, you are now required to monitor that start circuit from your transfer switches to your generator set. An interpretation of that is that it is only required on your Article 700 loads. That's up to your interpretation. But when you look at the engine start and monitoring, we will typically tell you that we're going to give you one set of contacts that will be through our monitoring system to meet that NEC requirement. We would typically then have a second set of start contacts that are wired directly into our PLC as a hardwire backup should you lose that communication also through the monitor system. The controls should be independent from the master PLC. Yes, they are. We'll talk about that. Loss of communication to the PLC or the system HMI does not affect the operation of the generator. Let me touch on that right now. If I lose my master PLC, I am still going to start the generators. I am still going to parallel the generators. However, since I've lost my load control portion by losing my master section, my master control, I will be able to transfer my priority 1 loads. However, no signal can be sent to the priority 2, 3, and so on, releasing that hold and letting them transfer to the emergency side. We can discuss that in further with you if you have a specific application. So what happens if the generator PLC fails? Some status will be lost, but, okay, full automation still remains. The engine breaker will start and close because we are relying on the D-slick. Common shutdowns will still operate because they're hardwired into our system. PLC start-stop controls are hardwired, synchronizing on oncoming generators and close to the bus. All of that still operates. There is no manual intervention required by anybody, and the hardwire engine control switches allow the operator to start and stop engines manually if needed. The system master architecture, now we can communicate with the ATSs as we spoke to, the breaker open and closing. Generator PLCs, we are communicating back and forth with those. We can communicate with the third-party switchgear. There is no problem. We may need some contacts to know what's opened or closed. The system HMI screen, number 1, you have in the master control section. We're going to show you a little bit later on. That screen can be duplicated in more than one additional place, which what we call a remote OIT screen. Why would you want that? Well, the gear is down in one section of the building, but your engineering people are in another section, and they would like to be able to see what is going on. All of that can be considered. The only thing I want to counsel you on is that we would like to discuss with you, we need to discuss with you distance. Distance even from the transfer switches to the paralleling gear. When you run Ethernet, Cat5, Cat6 type cable, you are limited to around 328 feet. If you exceed that, now we're speaking fiber. The reason I point that out to you is that can be something overlooked. It can be overlooked in the plans and specs. It can be seriously overlooked by your installing contractor who tells you, I didn't have any fiber in this. You didn't show it. Well, why am I requiring that? If I'm on the ATS, it's coming down to where the paralleling switchgear is. I may need to convert my signals from Ethernet to fiber, run those down to the area, and then convert it back to Ethernet so that I can communicate with it. A very important point with that is the fact that if you are working with automatic transfer switches along with the paralleling gear, you have a remote annunciator somewhere in your facility from each of your generator sets required by the NFPA, whichever one you have applicable. If you are an IBC code building, an international building code, if you are considered to be a high rise building is 70 feet or more above grade. That's as high as a fire truck can reach. You are required to have the remote annunciators in the fire command room for all of your transfer switches also. Please look into that if you're not familiar with that. Why do I point that out? Well, we're talking paralleling switchgear, I understand, but you may need to run fiber cable between these communications. We can discuss that further in here with you as you need to. We typically are communicating Modbus. If you need some other protocol, I see BMS on here. If you need BACnet or one of those others, you need to specify that. More importantly, who is responsible for the translator between Modbus to your BACnet facility? Is that by the Johnson Mathis people? Is that by Schneider? Who is responsible for that? That can be a very serious issue later on that nobody was held responsible for it. The EPMS, the Emergency Power Management System. We would love to present that to you. It is not only how the system operates, but it is a means of monitoring everything that you can see what's going on. We can also, through some other avenues, give you control in some remote locations should you want to operate breakers or do so. The system master can either be, as I stated, the single or redundant PLCs, as you can see. You notice now we still have the analog meters shown, okay? Depending on your specification, do you just want those now in that digital screen where you can scroll through it or such? The two annunciation panels that you see above the meters in the upper right hand corner, I like pointing these out because when your electrical contractor doing the installation says, how many wires do I need to pull? And we tell you, please give me 2 Ethernet cables, give me these shielded cables for each of the bias runs to the governor and to the voltage regulator, but I also need 20, 24, number 12 wires pulled between. Why? Because it is coming into these annunciation panels. It is making sure that shutdowns and pre-alarms to not damage your generator set are active and they are directly into the system. The master PLC is a key component. HMI is a human machine interface. OIT, operator interface terminal or such. This allows you to adjust some parameters. You know, that's very important. You don't want to have to call a tech out just maybe to set a timer from 5 minutes to 15 minutes or so. All of those types of parameters that you can do in the field yourself are password protected, but we can give you a list of those, okay? It allows the operator to perform a system test. System tests can either be online or offline. Well, tell me why I'd want to do either. I've done some maintenance to my generators. I've maybe changed out some batteries or a starter or something. And all I want to simply do is test the system, get it to parallel between each of the generators, but I don't necessarily need to go online. I just want to do that. That is a capability. There is also in all of our transfer switches a system that we call feature 17. This is what we use in our paralleling switch gear. If you want to do a test online, we are going to close the contact into our feature 17 option. What that is going to do is tell the generators to start and run, and it is going to transfer the load onto emergency even if normal is available and acceptable. When you're finished with your system test, please remember to come off of that, let it go into its cool down timer, and shut the generator down. When you look at what's in front of you here with this OIT screen, it is a dynamic one line. As situation changes, as your generators go from stop to start, as breakers open and close, that is indicated on here. You also have metering, alarm, shutdowns, historical trending. Okay. We also are able to give you a device within this gear that can do your JCO, your Joint Commission reporting. Okay, that is something that is available when you start your test. It will generate those reports for you. An EMS, EPMS interface is obviously okay. We can work with that. When we are working in hospitals, data centers, maybe in some type of 708 facility or such, we need to work very much in coordination with the IT department. Okay. We need to know, can we get on their system or do we need to stand alone or such? There is different levels of some type of password protection so that not just anyone can get into changing things. If we lose our screen, we do not lose functionality. You may lose some visual, but you do not lose any functionality of the paralleling gear. A little deeper dive into this, upper left-hand corner, that's the dynamic one line that I spoke of. On the middle side here, that's your alarm summaries. Then you have the historical trending. You may have genset controllers. We typically can read all of those, the Kohler, the Cummins, the Caterpillars or such. The screens there, red, yellow, and green, that are still those status panels. Very quick to look at. When you go to our system test at a factory, or if you pull this screen up, you can't see it very well, but each of those blocks will tell you which PLC is in control, which LAN is in control, if something has failed, and it gives you all sorts of status. And then on the bottom right hand corner are the reports that we're able to generate for the Joint Commission. There is an event playback here that you can look at, and a little simulation here as to what it's doing. You may want to look at this and see, well, what caused the outage? How did I respond to it? What happened? What did I go into and such? And each of these you can go into a dynamic playback. We're able to give you that function should you want to. The OIT screen is kind of have you see, it's either a 24-inch or a 42-inch type model. And again, I know that we can put at least 2 or 3 of these on the system or such. The top point I made a little bit earlier, but you may want to consider additional monitoring or controls to allow the user to get out of the arc flash zone. Monitor and control are the same as the HMI screen, and connection through is via the fiber or redundant fiber ports. Power control systems architecture. A single master PLC failure in a system with redundant PLCs ends up with no loss of automation. Generators, PLCs are independent as stated. Loss of communication from the master PLC to the gen PLCs do not affect the generator PLC's automation. However, as I stated before, should you have a catastrophe and you lose both of your master PLCs, the engines automatically start, and because there is no transfer inhibit signal to your priority 1 loads, they will transfer. The master control architecture and manual paralleling. I even saw a spec recently that still described a swing panel. Swing panel was a panel that if you were standing a couple of sections over, you could swing it over. There were 2 big white lights to it, and you watch that as you were trying to manually synchronize a generator to the other one. In our case, what we have is you are standing in front of the master section. You notice there is a green button there that says manual parallel. It works a very similar way. With the 2 white lights that we previously used to use, when you were 180 degrees out of phase, they glowed the brightest. When you were completely in phase at a 0 crossing, they went out. The green light here on our button works the same way. You stand there, you're away from the breaker you're closing. When the light goes out, you can press the button and manually parallel the one unit to the other one that you were trying to do. A very important point to it is the fact that if you're looking at that synchronoscope, it has to be moving in a direction very slowly. If it is moving too quickly, you're completely out of synchronizing. I cannot get in that acceptable window long enough for me to operate my closing. We do not, obviously, as you know, do not want to close out of phase. We don't want to damage either the generator or any type of downstream motor load or something. One of the other things that ASCO provides to you is a DC power system. The DC power, on the case of low voltage 600 volt gear, we are going to utilize the batteries off of each of your starting generators. We're then going to bring those into a DC bus that runs between all of the sections, and in our case we provide to you a best battery selector and a DC to DC converter that is there to make sure you have enough voltage, DC voltage, that you keep all of your PLCs, all of your protective relays up during the cranking period. If you're not familiar with that, when you have starting batteries at 24 volts and you're cranking that engine, that generator set, you can get down to a very low amount, lower than maybe 18 volts or such. And if it's too low, the PLCs can potentially drop out. Critical components, as we stated, are 18 volts, very much needed to remain online. The best battery circuit determines the best battery voltage to keep it up. The DC to DC converter is boosting the DC voltage. Uh, that now, when we look at low voltage 600 volt gear, we may not recommend to you a set of station battery systems. In a future presentation here with medium voltage, we would typically always give you some type of a station battery system, either 48 or 125 volt DC. In the case of low voltage, we will be utilizing the starting batteries, and you may not require any type of additional battery station. What happens when the light goes out? Well, what happens is that all of the generators will start, as I stated. Priority 1 loads will go, and then as you step this on, you notice priority 1, 2, 3, and 4 in our illustration here. You notice on the left side, we're putting all of those loads, priority 1, 2, and 3. Each one of those is a complete single step. Well, you may not be able to do anything about the priority 1 loads. You may need to step those on, and sometimes those are small loads. Life safety may be 100, 150 amp type circuit or such. But as you go up into the priority 2 and 3, 4, you may end up with chillers or larger horsepower ventilators, okay, motors. When you're working with your genset manufacturer, you know that there's only an acceptable dip and recovery that you want each time you add a load. In the case of this here, you would then set the priorities further up, priority 2 and 3, that you put chiller 1 on. You may wait 5 to 10 seconds, put chiller 2 on. Each time you do that, you're giving your generator time to dip, recover. Most of the sizing programs that I've seen, the acceptable dip is about 20%, unless you're looking at a fire pump application. Then you're limited to a 15% voltage dip. Please check me on that. That may have been updated some since I saw one of the programs. All loads cannot be connected immediately. We understand that. Master PLC loads connected to the emergency bus in a priority order, and that is set. That is set when the technician, when the startup is out there and he is putting the priorities in. We're going to look at 2 different ways how that amount is set. Power controls automatically. What happens if an engine fails? It depends. Traditional systems used to shed the lowest priority block. Current systems do not, unless they have to, okay? The system has what's called a load latch function. And that load latch function says, I have this much capacity online, I have this much load online, and I look at the next transfer switch to either have to be shed, or if load has been shed, can I re-add it? If you have enough capacity, your N+1 system or such, or depending on what time of day your outage is, when you lose a generator, nothing may happen. If additional load starts to get added because you've started your day cycle or such, the generator will automatically start and come online. If sufficient capacity remains, the load latch ensures that the loads will remain online, preventing any type of unnecessary disconnection and reconnection. All right, so we look at load demand, these two terms, and I'm sure Mumtaz would like to speak to you in depth about this as your projects come up. This maximizes the efficiency used by the standby generators. It disconnects the unnecessary generators. This is highly specified. In the case of many of the areas now, two things. Number one, diesel fuel or even natural gas fuel is expensive. Secondly, you may be in an area where you're concerned with the amount of emissions or such. As I stated before, just to make sure you get the emergency power up and running, all generators will start, they will close, okay? After a period of time, and that time can be set, we say we don't need one of these generators, we don't need two of the generators, and we will retire those. They will be available for automatic starting again. Bus optimization. This connects the number of blocks. Okay, it maximizes the load connection and it calculates if the next load block can be added. In this case, you need to understand how this works. I believe it's pointed out on the next slide or so. But in the case here, when you look at your ATSs, I understand you look at them. You put down that this is an 800 amp load that's feeding, 800 amp transfer switch feeding this 800 amp load. Well, what's really on there at any time of day? So if I take that 800 amps and I say, okay, fine, I'm going to say this is a 400 kW load and hard code that into the ATS, that's the number I'm using to know if I have to add or shed that amount of load off of the generator. The other term that we're going to delve into is called dynamic bus. Okay. What we do now is we also introduce a power meter on each of the transfer switches, and in lieu of just a plug number, the 400 kW or such, historically it's looked at and said, yes, you told me 400, but I really know there's only 230 kW load. That's the number that we use in order to do this priority load block. This should be something you should consider and discuss with Mumtaz. In this case here, we lose our utility. The first generator comes online, and those immediately go. The second generator comes online because it's available, and again, it immediately transfers. However, the third generator failed to start. So we look at this and we say we have enough power that we can close these two transfer switches on, even though they're a priority 3 load. If the other generator, in this case, the dynamic bus, if you can add all of those, you do add all of those based on. So going back to here, bus optimization, we have a hard-coded value in here. By doing dynamic bus, we know more specifically what those loads really are. And in this case, we were able to put all of the loads online, even though one of the generators did not start and run. Dynamic bus optimization measures the real time KW, and it's a feature that is typically underspecified. When you look at the power control section of a low voltage distribution, number one, I stated if they're electrically operated, you may lose one of the cabinets that you can put one of the breakers in. We have obviously those pistol grips that are an open close indication of each of the breakers. We can house some type of a power metering for each of those in there. You may still require an analog meter. And then the ERMS switch that's down at the bottom. If you're familiar with that, should you be in the gear working, you would set that to on. Two ways we can do that, folks. We can either do it for each individual breaker, typically 800 to 1000 amps or above, or we can just give you a system switch that when you want to do maintenance, you put the ERMS on, and I've effectively put all of my breakers in that minimum setting position for safety features. Just work with us on that. Different types of layout. If you look in the upper left-hand corner, that's a master section. There are a dual gen section and a simple set of distribution. Okay. The little device on the top there is when you're NEMA 1 indoor, we're going to offer this little overhead lifting device that you can use to remove breakers from each of the sections. Over to the upper right hand corner, now you see that we have a master section. Notice one thing. We've got a generator section with the distribution in the middle and another generator on the other side. We will work very extensively with this on the layout. Why are we trying to do that? It's pointed in the next couple of slides. We are trying to minimize the amount of main bus. In the case of paralleling switchgear, we can go from 3,000 up to 10,000 amps per bus segment. Why do I say per bus segment? If you have more than that, I have a 10,000 amp segment. I have another 10,000 amp segment with maybe some type of a tiebreaker, 5 or 6,000 amps or so. Okay, but we are limited to 12 to 10,000 amps. Why do I point that out so emphatically? Depending on if you're trying to flow all of your power one direction, you may exceed that ampacity. We'll indicate that in a little bit. Down in the bottom right hand, on the bottom section, can just get quite extensive as to how many sections can be lined up and, overall front view of that type of a lineup or such. So just a minute ago, this is taken from a different presentation if it looks a little different. First of all, when you're doing 891 construction, okay, I didn't point this out at the beginning, but the difference between 891 and 1558, I touched on the breakers and such, but 891 construction is limited to 6,000 amps. 1558 construction is up to 10,000 amps. Give me a little better reference of this. 891, you folks may think of it as switchboard. 1558, switch gear. Now, what may confuse you is even if I give you a piece of 891 gear, many times in our title block, we still call it paralleling switch gear instead of paralleling switchboard. Okay, let's look at this illustration to what I'm getting at. I have 4 generators. Each of the generators can put out 1,880 amps. So if I add all of that up and I flow everything from left to right, I have 7,520 amps. Therefore, I need an 8,000 amp bus. Once I have exceeded 6,000 amps, I've just gone from 72 inches deep to 84 inches deep. That may be a problem in your room. So let's talk about a solution. If I take and simply put my distribution on either side, now I'm flowing current both ways. Mumtaz kind of reached out to me on this. In this specific application, I understand there's 1880 per generator going left and right as indicated. But in this specific application, there is only 3,600 amps of load on the left and on the right. Therefore, the 3,600 is flowing each way. If I had 5,000 amps of load on the right side, I not only have the 2 generators on the right contributing ampacity, but I have generators on that left side also flowing. And because of the size of the load on that end, I may still need to give you a 5,000 or a 6,000 amp bus. Another thing, when you're looking at stacking the breakers, low voltage. The maximum vertical that I can have is a 6,000 amp vertical. I may have an 8,000 or a 10,000 amp bus, but based on the trip units, we'll discuss that with you. I know your frames may exceed that, but if we'll look specifically with you at the trip units, we can see that we can stack how many of the breakers because we're relying on no more than 6,000 amps vertically. This is what I was pointing out to you. As you look into frame sizes here of each of the sections, up to 10,000 amp bus and 6,000 amp breakers, 1558 or UL 891, these are the dimensions that you can look at. And this can potentially cause you problems. We need to work that through with you. You can see down at the bottom that up to 6,000 amp main bus, 72 inches deep, can be either 891 or 1558. And then this states that the one for 8,000 to 10,000 can be 891. That's a bit, should be corrected to only 1558. The other thing I want to point out to you is that when you are laying out, and I really mean this specifically, NEMA 1, where is my conduits coming into? Are they overhead? Many times in your one-line diagrams, your single line, you show me things coming from the generators or from distribution, but I'm not really clear what you need to bring in from the top or the bottom. That's very important in medium voltage, but also something that would aid us in how we lay out sections or such. Front access, up to 4,000 amp bus, 2,000 amp frame breakers. That can either be some type of an I-line panel of some type or such, or there can also be busing in each of those sections where you open the door and you can connect, you can make your connections between each section or such. Notice the dimensions though that you get into now. 94 inches high, and in this case, in lieu of being 36 inches wide, you're 46 inches wide, up to 48 inches when you consider. Paralleling switchgear design considerations and applications. We've been talking very seriously about a single common bus. We point out something else to you. Most of this gear, if not all the time, we require rear access to make the terminations. When you put it up against the wall, you need to make provisions that we can get back there. If you're putting it in an e-house, a simple suggestion is that in lieu of a complete skin on the outside, you would put a set of doors where you can open the doors, make your terminations, and then close the e-house up. I've seen one application where it was in a cinder block type building, and the electrical contractor got quite ingenious by taking a part of the wall out, putting a garage door there where he could open the garage door, make all of his terminations in the rear, and then simply button it back up and close the door. Segmented bus, very much so in medium voltage, but depending on where we're looking at here, when you're looking at generators 1, 2, 3, 4, 5, and 6, if you have priority 1 loads on each of those buses, or you have your priority 1 load separated because it's exceeding 1 generator, then what's going to happen is the first generator that hits is going to close your priority 1 loads on bus A on the left side. The generator that hits first will close your priority 1 loads. As each generator comes online, it will add all of the loads, then evaluate to close the breaker, the tie breaker, and start retiring unnecessary units. The ring bus is probably the most reliable because if I lose a connection point at any part in the bus, I still have a complete topography all the way around feeding my loads. Open transition. Open transition is specifically that, break before make. In the case of our power breakers, in the case of our circuit breakers, we are totally reliant on a breaker that is very able to be 5-cycle closure repetitively, redundantly, okay? Closed transition. Closed transition is a make before break function. In the case of when we've spoken to you about the closed transition automatic transfer switch, that is a passive synchronization. You typically have your generator running a slight bit faster so that you have a zero crossing between your utility and your generator. I love to give this analogy. What do I mean by that? You're sitting at a traffic signal, you put your blinker on, the car in front of you has its blinker on, neither one is controlling the other, but you're going to see that they are going to just hit in sync at least a couple of times, and they're completely out of sync. In the case of paralleling switchgear, we are driving those signals. We are driving those signals from our generators through the M-slick to the utility, and we are doing closed transition. This is something very important to discuss with your local utility company. Some of the Public Utility Commission, the PUC rules say if I am on and off in 59 cycles, I fall under this criteria. If I'm closed for longer than that, now I have more protective relaying that needs to be added to my system. Many of the utilities also want to know where you're putting that system in, even if you're on and off within that short period of time. Closed transition and soft load. In every case that we have spoke about in this presentation, when you take the load and you transfer it from normal to emergency or back, whatever that load is on that transfer switch is hitting block load one time. That's why we would like to stagger that. Number one, your generators can't take everything at all at one time. Secondly is if you dump everything back on utility, you're going to have a very high demand charge, and typically those may be set for at least 1 year period. Soft load is exactly what it says. We're going to close. Normally, we are going to close the generators in a little bit faster, pushing against the utility. Immediately upon closing, we're going to pick up some minimum, some 50 kW or so. Why don't we just go in at the same speed? Because if we close at that exact, we may go into a reverse power since the utility is larger than the generator set itself. So we close a little bit ahead, 60.01 hertz or such. Immediately pick up load, and then over a period of time, we will come off of utility and onto generators or returning the same way. Extended paralleling with utility, again, peak shaving, curtailment, any of those. Many of the utilities are now reaching out. They have exceeded their capacity during peak time. I'm sitting down here in Houston, Texas, and we are under that criteria where they will reach out to one of your clients, one of your customers, and say, if we can give you 30 minutes notice, we want you to come online, either connect and go into an island type mode where you are completely off the system, or can you at least generate your first 500 or 800 kW of your system? Those curtailment rates sometimes can be quite good. At least here in Houston, Texas, I believe they were offering Rice University around $12,000 a month to be on call in that regard. Closed transition is a momentary overlap, as we've spoke about. Segmented buses, we've touched on that a little bit, and the reason why. You can see life safety on either side. Soft load, we just went into that before the slide, and the intention with that is you can run everything and not overload the generator on one block loading. Other bus configurations can be a bus split like this where you have the generators including a load bank on one side, where you can then remove that you can do that normally close. You can open that gen M breaker and you can load bank the generators or such. And the same thing also holds true on the right side, where if you do have utility, you may want to be able to island the generators while you are doing your load bank test. Let's speak about a load bank test for a minute. If I am running a load bank test on one of my generators, and I have an emergency power outage, okay, what I'm going to do is immediately send a load dump signal. What that is going to do is it's going to turn off the resistors, the portion of the load bank, which is nothing more than a big hair dryer, okay? But the thing we like to point out is when we are discussing with that load bank breaker, circuit breaker, feeding the load bank, we're not going to trip it. Well, why, Daniel? Because what we're going to do is we're going to turn the resistors off, but we're going to allow the ventilator fan to keep running to cool those resistors down so you don't damage one. That's something we can discuss with you or such. We can do main time main. We work very much in association with that type of a lineup or such. The switchgear considerations, we will give you a complete sequence of operation. We will write that with you. We have standard templates, standard boilerplate. One of the items that got added is that I'm going to put a load bank in there. And when I'm on this certain type of scenario, I want to adjust my load bank up or down so that I maintain my 30, 35, 40% on my generator while I'm doing my JCO testing. That may not be in our standard sequence of operation. We're more than willing to work with you on that to try to put any specifics in there or such. When you go to a factory witness test, this is what they're going to use. They're going to use the sequence of operation to operate the gear, including all of the scenarios should you have a failure. One of the other things that can be provided to you is we can offer you a simulator. It's a fairly expensive device, but if you have a very high quality system, a data center or some type of a high level healthcare, and you have a turnover of people and you want to have the ability to train, this may be very much something that you'd want to look into. So when you look at the arc flash, we spoke about that a minute. One of these is the ERMS switch. We can also do zone selective interlocking. We can work any of those with you. We can work in conjunction with third party, other types of systems downstream to do the zone select interlock. Okay. An instantaneous trip is less than available in the arc current. Obviously, you can see that. Temporary adjustments of the instantaneous trip setting to achieve the arc reduction. Those things can all be discussed in a little further. We also have our specification that we can offer to you. Yes.
Sorry, Daniel. I can take it over from here.
Okay. There you go. Yes, ma'am.
Yep. Thank you so much again, Daniel. I will
Yes,
be
ma'am.
sending out this presentation to everyone that attended. At the end of all my presentations, I include our suggested specs. This does have the Word document embedded in there. If you right click and just do open, and it will open the Word document for our suggested low voltage paralleling gear specification. Next slide. I always include this as well. This just has additional online resources where you can find our Revit families and white papers. Okay, and that was a lot of information to cover, so you guys might feel like that man on the right-hand side, but next Lunch and Learn, it'll be on May 2nd. We are going to keep paralleling switchgear going, and we're going to dive into medium voltage. Daniel touched on medium voltage a little bit earlier in this presentation, but we're going to really dive into the differences. And I forgot to mention this earlier on the slide, but this does not replace in-person Lunch and Learns. I'm still available. Daniel can fly into our area if you need a presentation on this or automatic transfer switches in person to your firm. We are still available for that. So keep a lookout for the invite for medium voltage paralleling gear. And then thank you all for attending. With this QR code and link, you can scan or click that link. I will be sending out the presentation again, so you will have access to that link, and that will take you to a survey to fill out, and you will receive your PDH. If you have any trouble accessing the link or the QR code, just reach out to me and I can email you a copy as well. And down there is my contact information, my cell, and my email for if you have any questions after this presentation. I know it was a lot of information we covered. Feel free to reach out to me and we can answer any questions follow up. Well, thank you all for attending.